Ever feel like whenever some new tech really takes off, it's like a tidal wave? Like suddenly you're drowning in new terms and information overload, just trying to figure out what actually matters.
Oh, yeah, totally.
Today's deep dive, we're looking at exactly that kind of moment. We've got this GTC presentation. It's basically laying out the whole landscape of AI, like where it is now, where it's going. This deep dive, think of it as your cheat sheet for that fire hose of info.
That's a great way to put it. We're cutting through the hype to the real meat of this major industry event. The core takeaways. What's fundamentally shifting with AI, the absolutely insane computing power behind it all, and then the advancements in the nitty-gritty, the hardware and software. Our goal here is simple. You walk away knowing what's essential, what's surprising, and what the big vision is, without getting bogged down in jargon.
Absolutely. And to do that, we're going to get into some really mind-blowing areas, starting with like the atoms of AI, these things called tokens. How are those creating this intelligence? Then we'll tackle this seemingly bottomless pit of AI's hunger for more computing power and the tech that's being built to feed that beast. Then finally, how all of this translates into stuff we can actually see and touch, like smarter businesses, robots that could be right out of sci-fi, stuff like that. So let's just dive right in. What are these tokens everyone's talking about?
The foundation here, the thing to really grasp, is that these tokens are the units AI uses to process information. Imagine them as like the tiniest Lego blocks that AI uses to build its understanding and then generate stuff. What was interesting in the presentation, they highlighted how these tokens take raw data, could be a medical scan, could be computer code, anything, and let AI do incredible things. Spotting patterns in astronomy data, maybe predicting a disease outbreak before it happens, understanding all the nuances of human language, even creating stunning visuals. Tokens, they're like the currency of AI.
That's a good analogy. So it's not just searching for info that already exists, like we used to do. It's AI actually building understanding from these basic blocks and then creating brand new answers. It's like instead of a librarian who just gets you a book, we've got an author who can write a whole new one based on what they've learned. This shift from retrieval to what's called generative computing, that seems massive.
Exactly. And this ability to actually create new content, new insights, that's the driving force behind this thing they're calling agentic AI. Imagine AI that doesn't just get your request, but can actually reason about it, figure out a plan, then use tools, different kinds of infotext, images, even sensor data to get it done. It's AI becoming a problem solver, not just a tool.
And they touched on this idea of physical AI, which really got me thinking. This is where AI starts to actually understand the physical world around it, which is crucial for robots, right? It's not just following instructions, it's grasping concepts like how things move, what happens when you push something, even just knowing that, objects don't disappear when you close your eyes. This is the kind of stuff, this understanding of our three-dimensional world that'll really unlock robots' potential. Now all this amazing intelligence, it has to take a ton of power. That brings us to this crazy demand for computing power that just seems to keep growing.
Right, that's the core issue, isn't it? What's holding us back from even more powerful AI? The presentation identified three major challenges. First one, the data problem. We need mountains of the right kind of data for AI to learn from. Second, the training problem. How do we teach AI at a scale and speed that humans just can't keep up with? We can't be hand-holding it every step of the way. And then the third one, the scaling problem. How do we make sure that when we throw more computing power at AI, it actually gets way smarter, way more capable?
And it's on that point, the scaling of computing power, where things have taken a really unexpected turn. The estimate now is that reasoning AI, the kind that can actually think through problems step by step, it needs like 100 times more computation than we thought before. 100 times. That's just, wow, what's causing such a huge jump in demand?
Well, think back to what we were saying about agentic AI, this whole reasoning aspect.
Yeah.
Take something as simple as, say, planning a trip with multiple stops, factoring in flights, layovers, all that. Reasoning AI, it doesn't just spit out the first answer it finds. It explores a ton of options, evaluates different scenarios, even double checks for conflicts, like, hey, does this connection actually make sense? This chain of thought process, plus exploring multiple options and verifying the results, all of that means the AI is generating a massive amount of those tokens we talked about internally, just to figure out the solution.
So it's not just a quick guess, it's like showing its work, exploring different paths to find the best answer. And to teach these AI models to reason effectively, they're using this technique, reinforcement learning, with verifiable results. It's like, give the AI problems that have known solutions, math problems, logic puzzles, that kind of thing. It learns by trying different approaches, getting feedback on whether it got it right. This kind of training, talking trillions of tokens, it needs incredible computing power.
Precisely. And all this hunger for computation, it's already having a big impact. We're seeing massive demand for the specialized hardware that powers AI, like Nvidia's Hopper GPUs, and there's huge excitement for their next-gen Blackwell chips. When they mentioned $1 trillion investment just to build out the data centers needed to house all this infrastructure, that really hit home how big this shift is. We're moving away from the general-purpose computers that used to handle everything to specialized hardware like GPUs, taking center stage.
What's really fascinating is that this whole revolution, it's built on this foundation of accelerated computing with NVIDIA and their CUDA platform really leading the charge. It's not just about having powerful chips. It's about the whole ecosystem that lets developers actually use that power.
Let's unpack CEDA a bit. It's not just software that makes the chips work. It's a whole parallel computing platform and programming model that allows developers to use the massive parallel processing power of GPUs. And we're talking about a wide range of uses, not just graphics. And on top of CUDA, there's this incredibly valuable layer, what they call CUDA X libraries.
Think of these CUDA X libraries, like specialized toolkits, each designed to speed up work in all sorts of fields, scientific and industrial. In the presentation, they highlighted some really cool examples, like QNumeric, which accelerates numerical computing in Python. That's huge for data science. And then there's QOpt, which helps solve super complex optimization problems, things like figuring out the most efficient delivery routes. Then they've got libraries for really specialized areas like lithography and chip manufacturing, rolling out 5G networks, gene sequencing, medical imaging, even weather forecasting, plus things like quantum computing, computational engineering, massive data processing, and physics simulations. It's a lot.
The scope is truly mind-blowing. And these libraries are being used all over different industries. Plus, the partnerships with major players like TSMC, Samsung, software giants like Ansys, Cadence, it speaks volumes about how important these libraries are. And the fact that CUDA is widely available on all the big cloud platforms and private data centers, that means developers everywhere have access to these powerful acceleration tools.
That widespread availability of CUA seems key. It means developers using these libraries can tap into this huge network of powerful hardware, making their software incredibly impactful. It feels like a real turning point. Now, while AI initially took off in the cloud, where all the infrastructure and research was, we're seeing it spread way beyond those massive data centers.
Absolutely. AI is not stuck in the cloud anymore.
Oh, yeah.
Moving into everyday businesses, changing how manufacturing works, powering the next generation of robots, enabling self-driving cars, even pushing the limits of computing at the very edge of networks. They highlighted a really interesting collaboration between Cisco, Nvidia, and T-Mobile in this area.
The cool thing about their partnership is the goal. They're trying to build the tech foundation to put AI right into mobile networks at the edge. Think about that AI that could adjust radio signals on the fly based on real-time conditions, what users need, using context, and what it's learned to make communication better in ways we're just starting to explore.
Making the whole mobile network smarter, more adaptive. And speaking of AI in the real world, self-driving vehicles have been a big focus for AI development, and Nvidia has been a major player in this for a while now.
They have. They've been providing the computing horsepower needed for every stage of self-driving development, from the huge data sets and simulations in the data center to the powerful computers right in the cars themselves. Their recent partnership with General Motors, that's a big step.
For sure. This isn't just about providing chips for self-driving cars, it's a deep collaboration. Integrating AI into GM's manufacturing to make things more efficient, their enterprise operations for stuff like design and simulation, and of course, the AI systems in the cars themselves that'll power their future self-driving fleet. What stood out to me, though, was how much emphasis they put on safety under their Halos initiative.
Yeah, with Halos, it's really a safety-first approach, and they're going deep. Rigorous testing of their hardware and software, even down to detailed code reviews. They're also focused on training the AI on all kinds of different data to account for different driving conditions and situations, and they're big on transparency and explainability. How does the AI make decisions? They want that to be clear. Their huge patent portfolio in this area and that whole Halos workshop at GTC, it shows how much they're prioritizing building safe self-driving vehicles.
And to speed up the development of all this AI for self-driving, NVIDIA is really leveraging their Omniverse and Cosmos platforms. Can you break those down for us?
Think of Omniverse as like a digital sandbox, but super powerful. It's a platform for creating virtual worlds that are incredibly realistic, physically accurate. And Cosmos, it adds this ability to create tons of synthetic data in these environments. So you can do things like model distillation, where a really complex AI model trained in the virtual world teaches a smaller, more efficient model that can actually run in a car. You can also do closed loop training, where data from real world driving gets fed back into the simulation so that AI keeps improving. That virtual to real connection, it's huge for making self-driving tech safer and more advanced more quickly.
Okay, so we've seen how AI is evolving and the huge demands for computing power it creates. Let's get into the next generation of hardware built to handle all of this, starting with this Blackwell architecture as a major part of the presentation.
It was. Blackwell, it's a huge leap in how these chips are designed, especially in how they can scale up performance within a single system compared to the previous Hopper generation. The new disaggregated NVLink architecture that allows for crazy fast connections between multiple chips within a system, and then the switch to liquid cooling to handle all the heat generated. Those are key innovations. They can pack more power into a smaller space, delivering what they're calling exaflops. That's a truly mind-boggling amount of computing power, all within a single rack of equipment.
The presentation made a really interesting distinction between scale up, which is making a single system super powerful, and scale out, connecting lots of systems together. The focus on getting serious scale up first, that seems crucial to their strategy. And all this raw power, it's mainly aimed at a specific task, and it's a crucial one, inference.
And this is where things get really interesting for understanding the future of AI. Inference, that's the process of the AI generating those tokens, coming up with an answer to your query. It's like the core function of these AI factories they're talking about. How efficiently that inference happens, it directly impacts how quickly and reliably AI can respond. And that affects the quality of service, how much money you can make, the whole profitability of these AI deployments. It's this balancing act between latency, how fast you get an answer, and throughput, how many answers the system can crank out overall.
That wedding seating arrangement example they gave, that was perfect. A basic AI might give you a quick arrangement, but maybe it's not the best, using relatively few calculations. But a more sophisticated reasoning model, that takes more time. It explores way more possibilities, generates way more tokens internally as it thinks through all the different factors to find the absolute best solution. Speed versus accuracy. And that higher accuracy, it costs a lot more in terms of computation.
Exactly. Now, running these super complex AI models across a system that could have like dozens, even hundreds of these powerful GPUs working together, that's a huge technical hurdle. They talked about things like tensor parallelism, pipeline parallelism, expert parallelism, all these ways to split up the work and keep everything in sync. And you need really advanced software to manage all that. That's where NVIDIA Dynamo comes in.
Dynamo, they're describing it as the operating system for these AI factories. It handles the crazy complex job of spreading the workload across all the GPUs, managing the KV cache that's essential for maintaining context and language models, and constantly optimizing performance across the whole infrastructure. And making it open source, that's a big deal. It encourages collaboration and innovation across the industry, like their partnership with Perplexity.
The performance numbers they showed for Blackwell, especially when you combine it with the new super fast NVLink 8 and NVLink 72 interconnects and using the FP4 data format, it's a huge improvement over Hopper. How many tokens per second, how energy efficient they are. When they said a 25 times improvement in ISO power efficiency, that's just wild.
And that Pareto frontier concept they brought up that really highlights how complex designing these AI factories is. With millions of potential ways to configure the hardware, you need an architecture that's programmable, really adaptable, so you can optimize it for different AI workloads and what business needs. The performance gains they're seeing with Blackwell, specifically for these reasoning-heavy AI models 40 times better than Hopper, that really shows what it can do for the most advanced AI tasks. And then, that comparison they showed, a 100 megawatt AI factory using Hopper versus Blackwell. Blackwell takes up way less space for the same or even better output. That really shows the scale of this progress. And get this, they're even using digital twins built with their own Omniverse platform to design and optimize these crazy complex AI factories. It's AI designing AI infrastructure.
That brings us to their roadmap, which is, well, let's just say it's ambitious. Blackwell is ramping up to full production, but we're getting an even more powerful version, Blackwell Ultra, later this year. Even more processing power, more memory, and faster data movement within the system.
And looking further out, they unveiled the next generation, codenamed Vera Rubin Love, that they named it after an astronomer coming in the second half of next year. Big advancements across the board. a new CPU architecture with much higher performance, a completely new GPU design, better networking, and even faster memory. They also clarified how they're naming GPUs from now on, separating the GPU processing die from the chip package, which will be important for understanding future announcements.
And beyond Vera Rubin, the long-term vision is Rubin Ultra, expected in the second half of 2027. This generation is all about pushing scale up even further, another big leap in processing power, going from exaflops to even more exaflops, plus a massive increase in data bandwidth. That visual comparison they showed, the sheer size difference between the current Grace Blackwell systems and what Rubin Ultra is projected to be, it was striking. And the projected improvements in both raw processing power and how cost-effective this stuff is, it's remarkable.
All that power in a single system, it all needs to be connected,
Huh.
especially as we're building these huge AI infrastructures that span entire data centers. That brings us to networking, where NVIDIA is pushing things forward with both their InfiniBand tech and their Spectrum X Ethernet solutions.
With Spectrum X, it seems like the goal is to take some of the best things about InfiniBand, like really sophisticated traffic management to prevent bottlenecks and really low latency, and bring that to the more widely used Ethernet standard. The fact that they've already got large-scale GPU clusters running on Spectrum X shows they're making progress. But when you start talking about truly huge AI data centers, hundreds of thousands, even millions of GPUs, the traditional copper connections just can't handle the distances and bandwidth needed. That's where you need long-distance, ultra-high bandwidth solutions, like silicon photonics.
And NVIDIA just made a huge step in this area with their first co-packaged silicon photonic system. This tech, it hits a crazy 1.6 terabits per second of data transfer using this micro-ring resonator modulator, or MRM tech. It's a joint effort with TSMC and other companies. This could be a game changer.
It sounds like it. Compared to the usual pluggable transceivers used for high-speed data, which suck up a lot of power and get super expensive when you're talking millions of GPUs, putting the optical connections right on the chip saves a ton of power and money. Using light to transmit data, they can get around the limitations of copper at these massive scales. That silicon photonic switch they showed, it's a real testament to this innovation. Potentially, we could build AI systems of a size we can barely imagine right now while keeping power consumption under control.
So we've dug into the infrastructure behind AI. Now let's shift gears to how AI is becoming a core part of how businesses run, how it's moving into the enterprise.
The big takeaway here is that AI and machine learning, they're completely reshaping the tech landscape for businesses. The old way of accessing data-specific searches, finding files, it's evolving into something where you can just ask AI agents for answers and insights using natural language, like a super smart search engine that understands context. We're also seeing AI agents popping up as digital assistants in the workplace and AI helping software engineers write code.
And to support all of this, NVIDIA has announced new DGX enterprise workstations and servers, things like the DGX Station and DGX Spark. They're designed specifically for the demands of AI in businesses. And they'll be available through the big computer manufacturers so more businesses can access this powerful AI hardware. And it's not just computing power. Even data storage is being redesigned for the AI age.
That's really interesting. It's not just about storing files anymore. It's becoming a more semantic system. The data is constantly being analyzed, enriched with knowledge. So users can ask questions and get intelligent, context-aware answers, not just raw files. It sounds like they're partnering with a bunch of companies in the storage industry to offer GPU-accelerated storage so it can handle these new AI demands.
And in a big move to make enterprise AI more accessible, NVIDIA is making their R1 reasoning model open source as part of their NVIDIA NIMs. Those are basically prepackaged AI capabilities. So companies can deploy advanced AI anywhere they need it on their own servers, in the cloud, and integrate it into their own AI agent frameworks. They listed a ton of major companies that are already using NVIDIA's models, NIMs, and software libraries. It shows how widely adopted and impactful this tech is becoming.
Finally, let's get into robotics and what they're calling physical AI. They made a strong argument that the time for robots to really make a difference is now. They can interact with the physical world, and they can help with those labor shortages that so many industries are facing.
The potential uses are huge: automating inspections and maintenance for infrastructure, streamlining manufacturing, self-driving delivery vehicles, even building versatile humanoid robots that can do all sorts of things. NVIDIA's approach to robotics, it's this three-computer strategy. One for simulating robot behavior in virtual environments, one for training the AI that controls the robots, and one that's actually on board the robot in the real world. So it's a constant cycle of learning and improvement.
To tackle the big challenges in robotics, AI generating enough data, designing AI that can handle complex physical tasks, and scaling up robot deployments, Nvidia is pushing their Omniverse platform as the core operating system for physical AI. They've added two key things. Cosmos, which can create an almost unlimited variety of realistic virtual environments for robot training, and Newton, a new physics engine developed with DeepMind and Disney Research. Newton is specifically designed for the unique challenges of robot physics, dealing with things like rigid and soft bodies, tactile feedback, and it's all accelerated by GPUs for fast, accurate simulations.
And this is a big announcement. They unveiled Nvidia Isaac Groot N1, which is a general-purpose foundation model for humanoid robots. It has this really cool thinking fast and slow architecture based on how humans think, so robots can react quickly and also reason through more complex tasks. Groot N1 can learn and adapt to different robot designs. It can do all sorts of manipulation tasks thanks to that advanced synthetic data generation and robot learning pipeline. And they're making Groot N1 open source, which is another big step towards faster innovation in robotics.
This rapid progress in physical AI, it feels like we're on the edge of a major shift. It could create a huge new industry. NVIDIA's approach, with its focus on simulation tools, training platforms, advanced hardware, and these foundational AI models, it positions them as a real leader in this exciting area.
This deep dive has covered so much ground, from the basic building blocks of AI to how it's influencing all these industries, and the really ambitious vision for the future of AI infrastructure.
Absolutely. It's worth taking a moment to think about the fundamental changes we've talked about. AI that can understand, create, and act. This never-ending need for more computing power to drive it all, the crucial role of specialized hardware and all the software that goes with it, and the potential for AI to change everything, from how businesses work to the very nature of work itself with these intelligent robots.
So to you, our listener, given how fast all of this is moving, how fundamental these changes are, what new possibilities, what new applications of AI do you see emerging in the coming years? How might this affect your work, your industry, even your daily life? It's clear that the AI revolution is happening right now, and we're all part of this unfolding story.